Yes, hi, this is Bernard Brault. I want to talk to you a little bit about a new RS-232 mirrored bit tester that I'm building. I built one in the past and I'm modifying it and making some changes, and there'll be more changes to come as well. So what you see here on the picture is on the left is a Beaglebone. That's like a small Linux embedded computer, very similar to Raspberry Pi. It runs Debian or something like that, but it's a Linux machine. And next to it is a Texas Instrument Launchpad. It's a microcontroller. It's a little faster than the previous one I used, 48 megahertz, 16-bit, and it's got a lot more resources. As you see, the chip here in the middle is no longer a DIP, so it's not something I'll be able to pull out and make my own board. So what I plan to do is just use the Launchpad itself, the entire development platform. So between the two, there's a couple of jumpers at what you see. So let me describe this. There is it's web browser based. The purpose of the Beaglebone Black is just for the GUI, for the web browser GUI. And what you see here on the left is the browser, and you can reset counters, and it sends RS-232 frames out, and it measures how many frames actually make it back through some kind of loop back at the far end. What's new is baud rate selection and duty cycle, and I'll describe that, the duty cycle. So the Beaglebone Black basically acts as a server, and it communicates with the Launchpad via I2C. Because the Beaglebone is the master, it gets interrupted by the Launchpad when it's time to update or the display on the left, and it's very responsive. And it sends commands to the Launchpad in terms of like what baud rate and what duty cycle has been selected. And the Launchpad responds back with basically the statistics that highlight the number of transmitted frame, how many were received, how many in errors, how many CRC errors, and it has a nice page, and more importantly, it displays also latency. Let me show you on the next page here. So there are three pieces of code. One is the JavaScript running on the PC itself. The script resides on the bone, and the Beaglebone is running an HTML web server that I wrote in a Node.js script. So there is a script running here that actually acts as a web server. And the second part is that it has socket IOs, and these are HTML sockets, and these sockets communicate directly to the counters here that you see, the 4 counters, and I'll show you a live demo right after that. And then there is communication here, and there is some C code running inside the TI. So the TI here is pretty much real time, within few microseconds, close enough to real time for RS-232 application. So let me show you a little bit of a live demo here. I think it should be running right now as we speak. There you go. And what I'm going to show you is also a logic analyzer on the left. There you go. Just going to make this a little smaller. Okay, so let me reset the counters. So as you see now, it's transmitting something like 1,000 frames per second, so 1 frame per millisecond. It's receiving all these frames because I put a local loop back, so I'll just pull the loop back out and you see what happens. I'm just going to move it in and out. There you go. And you see how responsive it is, right? So of course it measured a whole bunch of errors. Oops, let me push it back in a little better. There you go. And I'm going to sample the transmit. I have like a logic analyzer. I'm going to start the logic analyzer and collect some samples. Stop it, and let me show you here. If I zoom in, what you see up there are the actual frames. So the frames that I sent start with a byte, which is a AA byte right underneath the mouse here. They all start with A, then there's a frame number followed by a microsecond timestamp. Think of this as like some kind of a running clock, and it just increments by 1 every microsecond. And the last byte is a CRC for measuring errors. So frame number 1 is sent here, followed by frame number 2 and 3 and so on. And I'll spare you the 100 of them, but I'll get to the end of it. And there's frame number 100 right there, and 100 is hexadecimal 64, so that's why you see the number 64, which is a 100 frame, the timestamps, and the CRC. And after it's done, the next, what you see here, the pulse that you see right there, that's the interrupt telling the bone that it needs to come and fetch the data, because I collect the statistics on the 100 frames, and it sends a command to the bone, and that command right there is 03, and the 0 here could take value 0, 1, 2, 3, 4, and that's the duty cycle, and then 3 is the baud rate. So I'll show you the purpose of the duty cycle. I added the duty cycle for SCADA application, because in SCADA mode you cannot sustain such a constant, non-stop sending of frames like that. It just, for SCADA it doesn't work. It buffers information, sends it out in some slow shape, way or fashion, waits for a response. So if I show you here live, if I go to 50% duty cycle and I rescan this, alright, let's stop it. As you can see now, I'm sending, instead of 100 frames, I'm sending 50 frames in that time period. So as you see the counters right there, they're upgrading by 50 at a time. And this is the 50% duty cycle because the line is busy. The transmit line is busy 50% of the time. So here's a frame. You see a frame starts with AA, frame number 7, but then the line goes idle 50% of the time. And I can change that to 25%. Let's rescan. And now you see I'm sending only 25 frames during that same period. So if I reset the counter, you see I'm incrementing by 25. And you see now the line is only 25% busy. And I have a 10%. Scan that. Stop. And now you see between each samples I'm sending 10 frames. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The last frame is sent. And then the bone gets, this is where it gets the command for which frame rate is selected, a duty cycle, baud rate, and then the statistics are sent. But as you can see here, it's like only using 10% of the line. And it goes down to 1%. Let's rescan this. So at 1%, notice I'm going to reset the counters. I'm incrementing, and it's basically sending one frame at the time, and I'm only using the line 1% of the time. So you have to somehow trust me here that you could fit, you see this here, the frame there, you could fit 100 of these frames in that same period. So if I change the baud rate to 9600, 1%, basically sending a frame out more or less 0.6 second, like one frame per second. So that's going to be a very good way of testing SCADA. So let me scan this one at 1%, 9600 baud, and there you have it. See, so I'm sending, and here's a second later, sending another one, and that's what you see right there. I have some plans where what I want to do next step, and it's going to involve quite a bit of development. I'm going to have this is one transmitter and a far end loop back, and it sees what is, it looks for whatever is sent out to be the same thing as what it's receiving, and there is a timeout delay. But the next version will have 2 UARTs, so I'll have a transmit, 2 transmitters, 2 receivers, and the purpose of that is to be able not only to measure round trip latency, but to see latency going from point A to point B, and then a asymmetrical delay from B to A, because in teleprotection application it's very critical. Alright, so that's the Beablebone Black tester. Let me stop the recording. Thank you.